Hello everyone. So today we will look into another new aspect, and that is polydispersity index. So in the previous video we talked about the different average molecular weights that we use in order to calculate the uh, molecular weight of polymers. So today we will introduce to a new term called polydispersity index. Now what does that mean? Before explaining to you that particular term, let me talk about the magnitude of the values of the average molecular weight as well as the number average molecular weight. So when we talk about the magnitude, as I told you before, the weight average would have a significantly higher value than the number average molecular weight that we can easily realize from the fact that here we are talking about the weight of a particular polymer with a particular molecular weight, but in this number average we are talking about the number of the molecules or moles of that particular molecular weight with that particular weight. So when we talk about the weight, if we have a larger or a bigger chain present in that polymer sample, it will have a larger weight. So we therefore have a larger contribution from the weight average molecular weight in comparison to the number average molecular weight. Now, if suppose we have a polymer sample in which we get both the values equal, in that case, we need to understand the fact that all the molecules have the same weight. So that means it's a monodispersed sample. So that means depending upon the broadness or the difference in the value of the weight average and the number average, we can get a understanding about the nature of the dispersity in a particular polymer sample. And that is why this particular ratio, that is MW upon Mn, which is referred to as the polydispersity index, it actually gives an indication of the breadth of the molecular weight range in a particular polymer sample. So if the value is 1, this ratio value is 1, then that means it's a monodisperse sample. Otherwise, a higher value than 1 imply that it is a polydisperse sample. So it gives a clear-cut indication like how much polydispersity is present in a particular sample. So it is a rough calculation about the polydispersity of a particular polymer sample, and this particular ratio of MW upon Mn is what is referred to as the polydispersity index, referred to as PI, capital P, capital I. Now, degree of polymerization, this particular thing we discussed in the starting part of our lecture, okay, where I told you dP is the degree of polymerization, which is nothing but the number of repeating units, and M is the molecular weight of the monomer or the repeating unit. So if you know a polymer chain and if you know the number of repeating units in that polymer chain, you can multiply it with the weight of the monomer, you can get the molecular weight of that particular polymer chain. So as we know that we have an average molecular weight, therefore we can also talk about an average degree of polymerization as well. Now, how to calculate the average degree of polymerization? It's almost a similar formula that we use as we use the weight average and the number average. So number average is nothing but summation. Number average degree of polymerization is nothing but summation Ni. So instead of Mi, we have here the degree of polymerization, polymerization of that particular polymer chain. So summation Ni di upon summation Ni. So weight average, only thing is instead of Mi, we have those terms replaced by, in this case, degree of polymerization of that particular polymer chain. So pretty similar formula which you can easily comparatively try to understand. Now, if you know any of these values, you can calculate the number average. So if you know the degree average degree of polymerization, you can easily calculate the number average molecular weight by simply multiplying that value with the monomer weight. And similarly, when you multiply the weight average degree of polymerization with the monomer weight, you can get the weight average molecular weight. Okay, so this is a brief idea about the relationship between the molecular weight and the degree of polymerization. It might help you sometime some numericals come, or you might be asked to explain what's the relationship between molecular weight and degree of polymerization, so you should be able to answer that. Now this is a good picture. So if I ask you which is the monodisperse and which is the polydisperse, you can very easily say that. Just pause the video and just try to answer it. Okay, I know you have correctly said that this first figure is the monodisperse sample and the second picture is the polydisperse polymer sample. Very clearly understood uh, from the size of the polymer that is shown in that figure. Now, here we have to understand another important thing is the dispersity pattern, because just by the value of the molecular weight we cannot say what is the range of the molecular weight present in that sample, or we cannot understand the nature of the polymer sample, because if we talk about a polymer solution having a average molecular weight of 40,000, it might imply that the molecular weights that are present in the sample can be range from 20,000 to 80,000, or it can be from 500 to 100,000. So it's pretty uncertain to know clearly from just from the value of the average how like what all molecular weights are available in that particular polymer sample. So that's why it's very uncertain. So we need another important aspect, and that is the molecular weight distribution. So what is a molecular weight distribution? Molecular weight distribution is nothing but a plot between the number fraction of the molecule versus the corresponding molecular weight. So if we have a polymer sample, we plot the Ni, which is the same as we saw in the formula, versus the corresponding molecular weight. So when we plot it, it appears as a bell curve. So this is the curve that you get, Ni versus the molecular weight. When we plot, this plot is actually the molecular weight distribution. Okay, this graph is the molecular distribution, weight distribution curve. Okay, so the peak of this particular curve is actually the number average molecular weight, and then we have the viscosity, then we have the weight average molecular weight, then we have the Z average molecular weight, because that's the highest value, as we have already came to know from the previous video. So this is how the plot looks like. It's a bell curve. Okay, and let's look at another figure. So this is another molecular weight distribution pattern. So there is two graphs shown here. So if I ask you which is a kind of more polydisperse sample, so you can easily say that sample 2 is the most polydisperse sample, because it has a broader weight distribution curve in comparison to the sample 1, which is kind of more monodisperse sample. As you can see clearly from this figure that both sample 1 and sample 2 have the same number average molecular weight. So just by average molecular weight, we cannot say clearly about the nature of dispersity in the sample. So for understanding that, we need to have this molecular weight distribution curve. Okay, so that is where this importance of these curves come into picture. This is another figure again showing samples with same this Mn value, but their dispersity patterns are different. So as you can see, the value of the broader peak is this M3. This M31 is the broader peak. All the others, all the Mn values are pretty same in all these cases. So we can understand clearly the dispersity pattern more better from the what you say as the distribution curve. We can get a rough idea of the dispersity pattern from the polydispersity index, that is nothing but the ratio of mw upon mn, but still a more clear picture we can understand from the molecular weight distribution curves. Okay, so that is where the importance comes. So sometimes you might be asked to explain the significance of the molecular weight distribution curve. There you can use these three graphs to explain its significance. Okay, and here we have a table that shows for different processes what is the polydispersity index values. Okay, so you can see that when it is heterogeneous, the value is pretty high, and when we use homogeneous catalyst, we get a better dispersity index, that is more towards a monodisperse index value. Then solution, suspension, emulsion, polymerization all gives better polydispersity index values. Okay, so I hope you got a much better idea. This figure is just showing how the polymer samples looks like. So this is a polymer sample, okay, having n molecules in general. So you can see we have different lengths of the polymer. So if we classify them based on the length, we have these categories present, these different lengths present in this particular polymer sample, and each length has n1, n2, n3, n4. So this value that we talked in the number average molecular weight comes from these. Okay, so because this sample contain different molecular weights, and each molecular weights contain different moles of that particular molecular weight. So we can talk in terms of moles, or we can talk in terms of weight of that particular sample. Okay, so I hope you understood this concept of molecular weights, and I'll be giving you a PDF file about the numericals concerned with this particular topic. So any clarifications you need, you can contact me. Thank you.